let's talk about some characteristics of projectile motions. The range of a projectile is defined as the horizontal distance between its launch and its landing, how far it travels along the ground, not how far it travels through the air. In the special case of projectile launch and landing at the same height, we can derive something called the range equation, which is given here. The range is v0 squared over g, where v0 is the muscle speed, times sine of twice the angle of launch. This only holds for cases where the starting and ending height are the same. So let's derive that. For x, the x would be at any time v0 cos theta, that's v0x, all times the time we're talking about. And for y, it would be y0, which is 0, plus v0 sine theta times the time we're talking about, and then plus a half at squared, but of course a is minus g for y, so we have minus a half gt squared. And those are true at all times. If we want to take this time, when we've landed back on the ground, then we know that we're at the range, and we've taken the time of flight now. What's the difference between t and tf? TF is a particular moment in time, defined as the instant the ball or whatever hits the ground again. Little t by itself is the clock time. So for any time after launch and before the collision with the ground, we could plug in the value of t into this equation. But if we want to know when it hits the ground, if we want to put in the idea that it's hitting the ground, we've got to pick a particular moment. So that's where that came from. Likewise, when it hits the ground again, it's at 0, is v0 sine theta times the time of flight minus 1/2 g time of flight squared. Now, back in your algebra classes, when they told you to simultaneously solve, and what we're looking for here, if we go, we have tf as an unknown, and we have r as unknown. So we have two equations and two unknowns. We should be able to solve them, assuming there's no degeneracy, and there isn't here. And in your Algebra 1 classes, they probably taught you to always just try and solve the lower one first, and we'll solve the left equation for TF and plug it into the right equation and then get R out of it. That turns out to be bad advice in this case. It's easier if we look at the right-hand equation, the vertical equation, and we say that 0 is, and then we factor out the thing we're looking for, and we're left with other stuff. V0 sine theta minus 1/2 g TF. Why is that useful? Because the zero property of algebra tells us that if two numbers multiply to 0, then one of them must be 0. Possibly both, but at least one. So either we have that 0 equals TF, or we have that 0 equals V0 sine theta minus 1/2 g TF. The first one is kind of goofy. The first one says that it hit the ground at the moment it left the ground. The time of flight is 0. That doesn't make any sense. So we're going to skip that one. We're going to obviate or neglect it, and we're going to say not physically meaningful for our problem. So then we get that TF must be, and we just solve this other equation, we get 2v0 sine theta over g. And then we can put that here. So we get that the range is V0 cos theta times TF, which we just found was 2V0 sine theta over g. We can do some traditional rearranging of that. Let's bring the v0s together to get v0 squared. Let's bring the g on the bottom, and then we're left with 2 sine theta cosine theta. And if you've taken trig, this might be already burned into your brain, that is a trig identity. And so we can replace it with something it's equal to, and it turns out that the thing in green is equal to sine of twice the angle, which is the range equation we were looking for. So we're done. There's a fair bit of weird algebra and trig in there. Is this particularly significant? I think it's useful to be able to do. I think the AP committee likes to throw weird variants of this at you. At the very least, it explains kind of where some things are going on here. Notice what happens with the range. For low angles, it's very small, but as the angle gets larger, it gets longer, and then eventually for large angles, it's small again. For the low angles, it's small because the time of flight, since sine theta is small for when theta is small, the time of flight is small. And so it can't get much distance just because it's not in the air for very long. For high angles, sine of theta gets closer and closer to 1. That's going to give us long times in the air, but now it's hardly ever moving over to the side. The range equation is one example of giving out some of the symmetries we get for projectile motion. And remember that symmetry is really the root password to physics. If you understand symmetries, the rest of the physics becomes easy to understand, easy to remember, and easy to manipulate. All right. Since projectiles have a constant acceleration, they partake of all the symmetries associated with constant acceleration. This is most useful when the starting and ending heights are the same. And in that case, the following symmetries hold. Notice there are at least 5 of them. The highest point in the arc occurs at a location whose horizontal distance is half the total range. The highest point in the arc occurs at a time which is 1/2 the total time of flight. Those are both useful. You're at your highest point when you're halfway to your furthest distance and when it's half as long to the furthest distance. The speed at launch is equal to the speed just before hitting the ground. The velocity is, of course, opposite. The horizontal velocity is the same at launch and just before hitting the ground. And remember that saying the same is sort of a degenerate kind of symmetry. And the vertical velocity just before hitting is equal in absolute value to the vertical velocity at launch, but is negative. Also, the range equation gives us a different symmetry, which is the symmetry of the sine 2 theta equation. And that's kind of fascinating because it turns out there's a kind of curious behavior. This video, which is just made with Desmos and doesn't have any understanding of physics in it, it's just the range equation, plots out the trajectories for 2 angles always, and the angles happen to be a magic pair. If you look at them, like the ones given here, they add to 90. They are complementary. And you can see a couple of very interesting things as that angle is increased. All right, the first thing you should have noticed is that the complementary angles always hit the same place. That's kind of interesting, that if you fire at 80 degrees and fire at 10 degrees, you end up at the same spot on the ground. Second, and magically managed to pause it there, that was a bit coincidental but nice, notice that at 45 degrees, well, 45 is its own complement, so we only get one angle instead of 2, one path instead of 2 here. And as I play it, notice that that's going to be the greatest range. After that, the range goes back. All right, you can see that again as we go up. We hit 45, and that's the furthest the range is, and then it comes all the way back down. And we see that from the range itself, which, remember, the range is some stuff that we're not changing, sine of 2 theta. So to maximize the range, we would need to maximize sine of 2 theta. Sine of an angle is maximized at 90 degrees. So we have 2 theta equals 90 degrees. Theta has to be 45 degrees. Right? That's where that comes from. That's a very mathematically driven way. Where is it coming from physically? Well, as I said before, the time of flight, which depends on the sine, is low for small angles and high for higher angles. In other words, the more vertically we launch this thing, the longer it stays in the air. For low angles, it is not in the air very long, but it covers a lot of ground because most of its velocity is along the ground, so it hits one place. For high angles, it hangs in the air a very long time, but it makes very little progress because only a little bit of its velocity is directed horizontally. So when we put those two things together, we can get the same ranges for the complements. And then we can also see that what we want to do then is maximize both of them. We want to have as much we want to have as long a time with as much along the ground as possible, and 45 is the symmetric point that allows that to happen. This is just a picture of sine 2 theta. And so the range, these axes are arbitrary. Don't worry about them. The values don't mean anything, at least on the vertical. But we're saying that, again, at 45 degrees, we get our maximum. And we have what looks, of course, like a sine curve because it's sine of twice the angle there. All right, that it falls off, that the range. And it says that at 90 degrees, we have no range, just like at 0 degrees, we have no range. A baseball is thrown from point S in right field to home plate. The dashed line shows the path of the ball. Use a coordinate system with up at the vertical direction and left as the positive horizontal direction and the origin at home plate. So let's draw ourselves an origin. This is our origin. Upward is plus y, and leftward is plus x. That's a little strange, but they say to do it, so we do. For each of these, select the graph from those choices that best represents each of these things. The horizontal velocity versus time. Well, the horizontal velocity should be some initial value that stays constant. And the initial value should be positive because we're throwing from S towards home plate, which is in the plus x direction. Even though we're in the minus x part of the graph, it's the plus x direction. So we want a thing which is a horizontal line above the t-axis, and that is A. How about the horizontal acceleration versus time? Well, once we've let go of the baseball, there is no horizontal acceleration. Gravity pulls downward. Gravity, in fact, defines downward. And so, therefore, there is no change in the horizontal velocity, so there is zero acceleration. We want a horizontal thing which is on the t-axis. That is C. The vertical velocity versus time graph. Well, it starts off moving upward. It ends moving downward. Somewhere along the line it had to come to rest. It came to rest, of course, at this point. Coming to rest means crossing the t-axis. So we need a thing which starts with a positive value, ends with a negative value, and crosses the t-axis. And our best bet on that is going to be this. So we should pick I. And then finally, the vertical acceleration versus time. Well, the vertical acceleration is constant, but negative in this scheme. Why? Because we are accelerating downward, but we took plus as upward. So we need something which is a constant value but negative. We're definitely looking for this. So that is B. So ACIB, ACIB. There are a lot of other graphs here, but none of them correspond. They're physically meaningful graphs, but not for this situation. All right, that pretty much takes it for projectile motions. Our next thing up will be the last on kinematics, which is circular motion, things going in an orbit of a circle.